Okay, so I'm going to talk about some results about how moment angle, the polyhedral product splits up. And the introduction is all the examples I've given, in fact, I think all the examples I will do involve 2 points, because when it gets too big, it gets too hard to describe. So the question is there something that happens to this polyhedral product, which I gave you a construction in terms of colimits and all that, that allows us to get some information about what it looks like. So that's what I'm going to describe. In order to give you the description of these stable splitting, and by the way, stable in this lecture means one suspension. I don't want to have to write suspensions all the time. So when I use the word that there's a stable splitting, I mean after just one suspension, okay? So, some notation. We introduced something called the polyhedral product. I'm going to be using the notation that's in Buchstaben and Pano's book, but there's an alternative notation for all of this, where X bar and A bar have been described. I have to describe an auxiliary construction that's similar but different. The notation for that will be K is a simplicial complex, et cetera, et cetera, et cetera. And I'm going to write it down, but all that is happening, write down the definition for the polyhedral product, get rid of all the multiplication, and replace them with smash products. Now, to make that precise, you define something d hat sigma. In the past lectures, there was no hat. That hat is supposed to look like a wedge. Sigma, of course, is a simplex. And this is now the smash product. And M is this ubiquitous letter that always indicated the number of vertices. And just as before, yi is equal to xi if I belongs to the simplex. Oh, by the way, there's a little sloppiness in notation. I'll use the simplex to denote the simplex, but also the set of points, the coordinates in the simplex. I don't want to have to write bars around simplex to distinguish the two. And it's ai if I does not belong to the simplex. So that's what I mean by, that gives me the d hat sigma. And just as in the case of the polyhedral product, we took the union over the category defined by the simplex, the simplicial complex. We define this to equal the union over all simplices in K. If everything are CW pairs and whatnot, I don't have to worry about colimits or unions, et cetera. So this is the definition I'm going to take. So this will be an ingredient in this decomposition I'm going to talk about. The next notation we need, which again, I might be saying things that everybody's familiar with, but I want to have everything fairly self-contained. If I is a subset of M, then K sub I is called the full subcomplex of K indexed by I. The vertex set is the set I we started with, and the simplices I'll call it the simplices are simply simplices that have their coordinates restricted to I. Okay, that's that. So let me state a splitting theorem, which was done by Tony, myself, Fred Cohen, and Sam Gittler. And again, there should be a suspension in this, but I know it's not good to write down, but let me simply say after one suspension, stably, the moment angle complex is of the same homotopy type as a wedge over all subsets of M. Oh, I also left out some notation. What am I? Yeah. Oh, I'm sorry. So one has to be a little careful here. I'm looking at the pairs x underline, a underline. The original definition of that, I gave you an x for every point in M, but obviously I'm only concerned now with the x's and a's over the coordinates in I. And I take the smash polyhedral product for every full subcomplex, and this guy decomposes as a wedge of those guys after one suspension. Question?
Is this the topological version of the Hofstra model?
That will come out eventually. Yeah, that's good question. And the splitting, for example, for the suitable cases of a diskiness, D2S1 is going to give us the Hofstra formula. That's a very good question. So let me put this up here.
Excuse me, Martin. If you have a question, this allows those who are watching to hear your question. Okay. Thanks.
If you want them to hear your questions. And I'm going to leave a sketch of the proof. Oh, sorry, yes. If I put in the empty set, that's going to produce a point. I decided to leave it out. Yes, the empty set is a subset, but that just produces a point. So yeah, to be precise, I should put greater than or equal to the empty set. Thank you. Here's the proof, at least a sketch of the proof. If I take a product of space, I've used X and Y, Z, W1 cross W2 cross WM. So I take a product of spaces. Why is this interesting? Because XA upper K starts life as a product of spaces, which are X's and A's. And if I suspend that, this is going to break up as a wedge over all I contained in the set M. And what I mean by this is I take the smash product of the WI's indexed by the I. It's a simple fact about what happens when you suspend a product. And I want to emphasize it is natural with respect of maps of W to W primes. That's essentially the content of the proof, but I guess I should put in a little bit more detail there. Remember the building blocks for XAK, we call them D sigma, was a product, which I'll write this way, where the YI's equal AI or XI, or XI. If I suspend this, which of course is going to be part of what's happening, when I said stably, I'm suspending the guy on the left, so I'll be suspending these guys. This is going to break up into a wedge of, let me call it Y upper I, smash. It's going to break up into a wedge of pieces of this product corresponding to each subset I. Now notice, I said equal to AI or XI. I see an XI whenever there's a simplex, whenever I belongs to the coordinate of a simplex sigma. And then when I look at this, I will see sigma intersect I as the coordinate. I'll see an X in this smash product corresponding to the coordinates of any simplex restricted to I. So I see a wedge of these guys, and it's natural with respect to inclusions. As the sigmas roam around the simplicial complex. All of these things are going to be included into one another. We take the union, and it's natural. So for each of the restricted i's, this union is producing exactly, by definition, the smashed polyhedral product for that particular subscript. That's a sketch of the proof. But that's all that's really going on. But we have a problem, at least from my point of view. Let me get rid of this. We have a space on the left which we know nothing about. And I've just split it up into a bunch of spaces that I know nothing about. I've got more garbage on the left, on the right than I had on the left. We need some more information. So I'd like to spend most of this talk describing how we get information about the x bar, a bars for suitable x's and a's. And the lemma I want to spend some time talking about is called the wedge lemma. The wedge lemma is going to give us information about the pieces on the right, which will enable us to come to some conclusions, and I'll answer his question in the course of doing that. Okay. So let me describe the wedge lemma. All right. The wedge lemma gives us a lot of information about the smashed polyhedral product under suitable hypotheses. What is the hypothesis? Suppose the inclusion map of AI into Xi is null. An example, D2S1, the situation that gave us the the MAC. Then there is a decomposition. Oops, almost wrote a Z. And this breaks up as a wedge, but to describe the wedge, I have to remind you of some terminology from simplicial complexes. So if I have a simplicial complex K, and I have a simplex in K, then there is something called the link, in K of the simplex. This is equal to the set of all tau, such that tau is disjoint from the simplex. And again, I remind you, I'm using sigma to denote also the coordinates, the vertices of the simplex, as well as the simplex itself, such that tau union sigma belongs to K. So I want to give a few examples because they're going to be important. This is another canonical simplicial. There are only about 2 examples, I think, that ever have been drawn in the course of these lectures. 1, 2, and 3. This is K. The link in K of 1 is equal to 2, because 2 and 1 is a simplex in K, whereas the link in K of 3 is the empty set, because there's nothing I can add on that gives me a simplex. And very important, the link in K of the empty simplex is K itself. Those are the generic examples. Then this smash polyhedral product breaks out as a wedge itself, indexed by the simplices in K of the link oops, let me leave a little space. Take the geometric realization of that, suspend it, and smash it with something I'm going to call d sigma, which is similar to the d sigma I used to define the xik hat. And what is d sigma? You can almost guess. Well, it's exactly, I should call d hat sigma. I will just leave it like that. This d hat sigma was the smash product of x's and a's, x when it's in sigma, a when it's not. This guy decomposes as that, involves the links, and the d hat sigmas I had before. Right. And I could feed this into that formula where k sub I replaces the k. So the first thing I want to do, I'm going to save this. Eventually, not eventually, but shortly, I'm going to give special cases when dA is contractible or the x is contractible, et cetera. But I think I'd first like to give an example where the inclusion is homotopically trivial, but the space is not contractible, just to unravel all this notation. So example. Well, my God, I said the only examples we could do at 2 points, and guess what? Same thing. K is 2 points, which are cleverly called 0 and 1. 2 disjoint points, and x bar, a bar will equal S2, comma, S1, where S1 is included into S2 is the equator, homotopically trivial. Let us use the splitting theorem and the wedge lemma, which applies to this, to give you, after one suspension, the homotopy type of this guy. And in the course of doing that, hopefully I will illustrate what that thing really means. There's a lot of words and chalk marks, but hopefully it'll be clear after the example. So, to illustrate how the splitting theorem works and the wedge lemma, we have to list the i's, the possible subsets. And I'm actually going to put the empty set last. Sorry about that. Oh, I'm sorry, the empty set's not going to appear because, as I mentioned, it's a point. Well, I can have, what are they, 0 and 1? I could have the i's with just one coordinate. And I could take I equal to the full 0 and 1. So let's figure out what happens via the wedge lemma for 0. So I'm looking at I equal to that subset. What are the simplices in that subset, the sigmas that I could apply to k sub I? Now I do have to consider the empty set. So we have the simplex, which is 0 itself. And let me leave a space. And the empty set. If I take the link in so what have I done here? This subscript, if you recall, was the simplicial complex. For k sub I, it's 1 point. That's the simplicial complex. The link of the empty set is the simplicial, it's a point. It's a single point. And in the wedge lemma, I'll be smashing with the link. Smashing with a point makes it contractible. So this gives me nothing. Whereas, if I take the link, oh, I forgot an important point here. The convention, very important point. The suspension of the empty set is the zero sphere, because I'm going to use that, I left out that point. Basically, when I take the join with the empty set, I don't want to do anything. That's where that comes from. Sorry about that. So what is the link of this is the simplicial complex. That's my simplex. The link is the empty set. There's nothing there. So what do I get in the wedge lemma? Don't forget, when I take this suspension of the link smash d hat, the suspension, the empty set, it's smashing with S0, it does nothing. So the question is, what is d hat for this, in this particular situation? I'm taking the 0 simplex, and I'll emphasize this is the d hat for that simplicial complex. It's S2. The simplex is the point in the simplicial complex. And that means I'm taking S2 indexed by that point. So I get a copy of the 2-sphere. So that is telling me that I've got an S2 coming about because of the analysis for the 1-point set. Well, it's exactly the same analysis for, instead of taking 0, I take 1. I get another S2. These two copies of S2 come about by looking at the 1-point subcomplexes. Now let's analyze I equal to 2 points. Well, for I equal to 2 points, what are the simplices? Remember that wedge is over the simplices. I've got 0, 1, and the empty simplex. Looks very similar to what we just did. So when I do 0, very similar, link in I, by the I I mean these 2 points of 0 gives me the empty set. If I take the, oops, I should put a 0 around there. There's no other simplex I can add. That gives me the empty set. So I find myself in a very similar situation where I'm going to get d hat of 0 for this I, because I'll be smashing with S0 in this case as well. But now what is d hat? Don't forget I'm in I. It has 2 vertices. The simplex is 0. I get an S2 from the 0, but then I have to smash it with an S1 for the other simplex. I get an S3 this time. What about link in I of the empty set? That is going to give me 2 points. Remember this, you get the simplicial complex. So I'm going to get 2 points. That's an S0. And then I am smashing that. I'm taking, sorry, I get S0, the suspension of S0, smashed with d hat for the 2 points. So for those, but the simplex is for those 2 points. What is d hat for the empty simplex? Both vertices, the only vertices that are, there's no vertex that is in the empty set. I get S1 smash S1 because both vertices are not in the simplex. So this is going to give me an S2 because d hat is S1 smash S1 in this case. I get an S3. I've got an S3, an S3, and if I did, I'll get another S3. So hopefully that wasn't too fast, but the wedge lemma gave me 2 copies of S2 and 3 copies of S3. If I, by the way, if I then computed, and this is after 1 suspension, of course, it's all stable. If I computed the homology of that particular, if I computed, oops, I forgot to put the smash, oops. If I computed the homology of this thing, I of course can use the Viatora sequence to do it in this simple case. And thank God you get the same answer. At least you don't get a contradiction. But that's how the wedge lemma works. It allows us to take complicated situations and actually crank out the actual geometric splitting after one suspension for the moment, for the Z hat, the smash polyhedral products, which are the input to the actual polyhedral product. So that's an example. Now I want to do some special cases.
It's the wedge of all of those. The wedge of all of
Oh yeah, that's what I meant. You get a copy of this. It's the wedge of all these that fit together in the sense of the wedge up there. Okay, hopefully that was reasonably clear. Okay, so now some special cases. Excuse me? Perhaps I shouldn't have erased it so quickly.
No, yeah, it's just a question about the notation on the top. It says like XA wedge simplicial complex. But that simplicial complex has,
Excuse me, I'm sorry.
oh, the notation on the top?
Yeah.
That it says X comma A wedge,
Wedge.
smash KI.
Yeah.
But KI is a thing on size of I vertices.
The
XA
K sub I, just to recall it, we called it the full subcomplex. I have all my K, which has like 25 vertices. Pick I to be some set with 3 vertices. This would be the simplicial complex in those 3 vertices.
Right.
And the simplices in that simplicial complex are obtained by restricting simplices in the big complex to those 3 points.
Yeah, but the thing is, that thing is on like those 3 vertices, and X comma A are M things.
I made some I made the comment, I should have said again, I should have a sub I there.
Oh, okay.
I said earlier that there's X and A for everything, and that notation is meant to imply is the X and A restricted
sorry,
to the
I
vertices
didn't
in
hear
question.
that.
So does that help?
Yeah.
Thank you for asking the question. Okay.
comment.
Uh,
In that notation, where you have in the exponent smash Ki, the usual meaning of that notation is I'm going to take a smash product of all the Ki's over I.
right, but I'm following.
Exponent notation.
Yeah, but I'm using the notation in the various books for the smash polyhedral product. That's a notation that I found. But there are other notations which might be clearer, but at least I think I defined that. Yeah, but I defined that symbol for any K to be, that Ki is supposed to be a simplicial complex, and that notation means the smash product the smash polyhedral product for that simplicial complex. Oh, no, that doesn't define, that's the wedge lemma. This is a theorem that tells me how to compute that under special cases. Okay, so now some examples. Special cases. Suppose the AIs are contractible. So it's xi comma a point, for example. Let's take a look at what the wedge lemma tells me. The decomposition plus the wedge lemma, I'm going to be looking at things like the link of K of some simplex suspended like that, smash D hat sigma, and I'll put a sub I here to indicate that this is the appropriate definition of this for the I. Now take a look at that. Oh, I forgot to put, and there's this, yeah, take a look. This thing will be contractible most of the time because I do not want an A in this smash product. In this D hat, there's X's and A's, but the A is a point. So I cannot have a vertex that is not in the simplex and in I, because otherwise I'd be smashing with a point. So that tells me that sigma has to equal I. It's the only way I could get something that's non-zero there. So if sigma equals, I should put a K sub I here. If sigma equals I, this is the link of the whole thing, and sigma is the whole thing. What is the link in K of K? It's the empty set, because there's nothing else out there. So this is going to give me, the empty set is smashing with a 0. It's going to give me xi, x1, smash xi1, xi2, smash xit. With these subscripts are the subscripts in I. So the only way I will get a non-zero element here is if this is a smash product and I belongs to K. That's the only way I'm going to get something non-zero. Well, let us compare that with something we know. I'm going to put it all together. Putting it all together. If I take Cp infinity, comma, a point, upper K, and feed in this information, what I'm feeding inward to any x, but I'm just going to do it for Cp infinity, I'm going to get a wedge over the simplices in K of where these Cp infinities are sitting over the vertices of the simplex. So you see a product of Cp infinities corresponding to each simplex in K. Now, Don talked about the Stanley-Reisner ring. He told us that the cohomology of Cp infinity, comma, a point, up a star, was the Stanley-Reisner or the face ring of K, which, if you remember, was the polynomial algebra on generators V1 to Vm divided by an ideal generated by non-simplices. What I mean by this is monomials indexed by the non-simplices. Well, what does this look like as a group? If I look at the monomial basis, I would see monomials for each simplex, because I've killed every monomial which is over a non-simplex. But that's exactly what I would get here if I took its cohomology. I would see monomials, if I did the cohomology, reduced cohomology, I'd see a monomial index by subscripts, which are simplices. So it agrees what we got. As a group, it gives exactly the same answer as the Stanley-Reisner ring. Again, that's a nice bit. If that were not true, we might as well all go home. So that's one example. Now, the next example that I like to do is the case xi is contractible, e.g. d2 s1. Let's see what happens in this case. Again, let's take a look at the kind of links that would show up. So what do we have to avoid this time? The sigma, this thing will be 0, that thing will be trivial every time there's a coordinate which has an xi in it. So anytime I have a simplex, a non-trivial simplex, which has a coordinate which is going to give me an xi, that thing's gone because it's contractible. The only sigma that will produce a non-contractible term here is sigma equal to the empty set. So the only thing I'm going to get, I did put geometric realization. And if it's the empty set, I'm going to get a copy of, I'm going to get a copy of AI over each of the vertices in the empty set. And I'll write that this way. So it's AI1 smash AI2, et cetera. And what is the link of the empty simplex in K? We've done this already. That's K. I'm sorry, this should be the, I'll put a k sub I here in I. So the superscript here are the vertices in the simplicial complex, which are I. So in this case, I get the suspension of the underlying simplicial complex smash the AIs smashed together over those coordinates. Let's take the example of D2S1. I don't need this anymore. The example of D2S1, homology or cohomology. I'm doing the, let me just give this, let me actually give the decomposition. And don't forget, this is stably after one suspension. I'm going to get a wedge. It'll be wedged over all I. And the contribution of each of those factors over there using the wedge lemma in light of that interpretation is going to be the suspension. Now the A sub i's are all circles. If I take a circle and smash it together, or indexed by I, I'm going to get a circle, the dimension of, I'm going to write number of points in I. Those are that's what I would get. And of course, I prefer to put it like that. If I take cohomology, so the cohomology of the MAC is a sum, reduced cohomology, of the cohomologies of full subcomplexes, and there's a suspension factor. Now, Don wrote down that theorem, Hochster's theorem. He left out the suspension factor, but that's there. This is that's a geometric version of Hochster's theorem. Comes out of this. So those are some important examples to illustrate how the wedge lemma helps us. Now, what I'd like to do is give some, there's one more example, a very important example. I'll put it up here. Let us take the interval, comma S naught, upper K. This particular one. Again, after one suspension, what would this give me? This would give me, it's of this type, where the D2 is replaced by S1, but these A sub i's are all zero spheres. If I smash with zero spheres, nothing happens. So as a special case of this, the polyhedral product for, maybe called the real moment complex or something, IS naught upper K is just a suspension of K. What I'd like to do, maybe it'll end it, I'm putting this in a box. That is the generic fact. Given that, I'm going to show you why I'm going to try to show you why the wedge lemma is true. And this is the information I'm going to feed into that. So, and the reason I want to go over this, besides, it introduces a technique that Tony, I, and Fred, and Sam used to analyze things that are called wedge decomposable. So I'm using that technique to sort of show you why the wedge lemma is true if I assume that fact.
But I think it's still a wedge of full subcomplexes.
Oh, yes. Right. Okay, let me do this. Smash K. Sorry, thank you. I didn't have enough coffee. Smash K is that, and you're right. If I left out that, I should take the wedge over all I. Thank you very much. That fact will be the input to the wedge lemma, which is a statement about wedge K. Now, because I'm running a little out of time, so I'm assuming I've got XA where the inclusions of AI into XI are contractible. I'm going to make a slight modification of that. Suppose I consider A smash the interval wedge x, comma, a. Oops. Using the fact that this is homotopically trivial and the fact that this is just a reduced cone, I could get a map from here to here. I'm not going to go through the details, which is a homotopy equivalence of pairs. The x just goes to the x by the identity, and this is going to the x by the homotopy. So I can use this because I mentioned in my first lecture that the polyhedral product is invariant under homotopies of the x's and a's. So the homotopy type of this will be the same as the homotopy type as that. So I'm going to use this guy. So what do we do? First thing we're going to do is write down what the d hat sigma is. What is the d hat sigma? Over the vertices, so to do, I'm sorry, there are reasons I want to use omega for the simplex. I mean, I've been neglecting all the other Greek letters. I'm going to use omega for the simplex. Omega belongs to k. So what is the d hat omega? Over the vertices of omega, and again, I'm using omega both for the simplex and the set, I take A smash I wedge X, and over the vertices that are not in omega, I take A. And if I now this I is the interval, not the subset, not a subset. And K is any simplicial complex on M letters. So I don't have to use I in two places because that would just screw me up. So M is the number of points in K. And I'm going to use difference notation for set difference. So I've taken omega out. That's exactly what I would be adding up. Well, what happens if I smash together, let me put a little bracket around this, wedge the two things, smash together omega many times. There's a distributive law. We call it the Cartan formula. But this would distribute. So this would be a wedge. I'd have some tau many products over here. I use tau. There are so many products that occur here. And then I would be smashing that by x raised to omega many, the remaining. This is, if I expand this, I get a wedge of things that look like this. And this is all smashed by A m minus omega. That's just the distributive law. But I'm going to rewrite this. Oh, and this is the wedge over all tau, tau contained in omega. So this is the wedge over tau. A, these are all smashed over here. I'm sorry, I keep on forgetting to do that. A smash A, I'm going to write I smash tau. A smash tau smash x smash omega minus tau smash A m minus omega. Just a distributive law, and I've hopefully put all the numbers in right. I could take this A smash tau and bring it over here, which I'm going to do. So I just rearranged everything. Now define sigma, this is a simplex, to be omega minus tau. Take that simplex. Notice sigma intersect tau is empty, and tau union sigma belongs to K, because it's omega. In other words, tau is simply an element of the link of sigma. That's all it is. So I've just renamed everything. So I'm going to rewrite that. I'll do it over here. I'll do it over here. So I can rewrite this thing. One minute. I just rewrote the d sigma.
Is that equal to the intercept as opposed to not equal to the intercept?
This,
Intersection of the two.
the intersection of the two is the empty set. Because sigma is omega minus tau. Which one, what's the problem?
It should be equal. It just looks like.
Oh, no, that line was left behind. It's equal to the empty set. Sorry. There was a scribble on the line. I should have erased that. So that's why tau is in the link. So I just rewrote what d hat omega is, and now I take the union over all omega to define the gadget I'm interested in, to define this guy. But first, let's take the union over the tau, and then over the sigma. That's going to give me the unions over the omega. But this is by definition that. That's a definition. If I take I comma S naught, take the union over tau, this thing here is the link in K of sigma by the wedge lemma that's literally in a black box. And this is d hat sigma. So in other words, if you grant the black box, you get the full power of the wedge lemma as a corollary. I have 10 minutes more. I want to point out why I went through the machinations of this proof. Certain pairs of space, I'd like to get some of this beyond the situation of the wedge lemma. I'd like to have some statements about pairs where it's not necessarily the case that the AI includes trivially into the XI. So one step beyond that are pairs U comma V, which I'm going to write as B wedge, I'll use a C this time. The B this is the homotopic to the identity, and E is introduced and goes into this as a contractible space. We call this a wedge decomposable pair. And exactly the same proof, nothing more than the distributive law, gives the following decomposition, which I will screw up unless I look it up. So give me a second. I wrote it down somewhere. Okay. The same proof gives, after one suspension, of course, everything is stable, a wedge over R. Oh, I'm giving you a formula for U and V satisfy that. Yes, okay, thank you for reminding me again. Do I want to say, this is actually, no, this is not the smash. So I'm putting in the wedge limit to each factor. So that's not the smash. So, okay, let me. Oops, I guess I end the bracket here. So where there is for a wedge decomposable pair, just using the distributive law, and this part is of course coming about from the wedge lemma and the argument I just went through. You can decompose this in this way, which gives a lot of information, but it's still quite restricted. So I'd like to end with what's, I think, an amusing step beyond this. Oh, and again, this is all in work with myself, Tony, Sam, and Fred. Suppose U and V is not wedge decomposable. I mean, life is not in general going to give you what you want. But suppose it is homologically or cohomologically, I'm just going to use those two words interchangeably, wedge decomposable. What do I mean by that? Suppose I'll use homology so I get the orders right. The homology of U, comma, the homology of V. So I'm going to look at this pair of homology groups, which of course, if it's wedge decomposable, I know what it should look like. Suppose this can be written as, and I'm going to use the same letters, but now these letters denote modules, K modules, where K is the underlying ring. I guess I better put a plus instead of a wedge. Where the B goes by the identity and E into C is the trivial group. Basically, I'm telling you what the long exact sequence on homology looks like. And we want to put in some freeness conditions. We can't get away with that. So we'll assume let's assume we're over a field. What the hell, make it a little easier. Then cohomologically, this is still true. Put cohomology everywhere for the things. You'll get the cohomology of the links, et cetera, et cetera. This is a calculation for the polyhedral product for UV subject to this condition. And it's highly non-canonical, the choice of the basis. I'm not making any claims about it. But in work that's going on was trying to use this to get some insights into the ring structure in the polyhedral product. But
That's always possible.
what?
That's always possible.
Well, as long as we have the freeness conditions, right. So this is actually quite general, subject to freeness. So work over a field, you can always do it. Good, I think I'll end 3 minutes early. Yeah. I'm sorry.
You mean that you have a similar homological decomposition in that case, right?
Right, so if we have wedge decomposable, it's clear how I would choose the B's and the C's.
Okay, so how do you explain that fact in terms of...
Okay, so how do I explain why the homological fact follows from that fact?
Gauss-field count spectrum.
Well, okay, so it turns out if one does it carefully, you can describe the let's work over a field. The polyhedral product, you want to know in what sense is it a functor of the X and the A's? And it turns out that you don't actually have to have a map between X and A and X prime and A prime. Suppose I have X and A and the cohomology decomposes in this way. I could pick it could do it with torsion as well, but that's not where I could pick spheres to represent the generators. I could make a wedge of spheres, which clearly I won't get a map between them, but they cohomologically will be identical and fit together in the EHP sequence. And, the suspension sequence, rather. I'm a homotopy theorist, I forgot. It fits together in the suspension sequence in the right way. And the theorem is that the polyhedral product is really a functor of what we call the strong freeness condition. Namely, there's a map between the long exact sequences in homology. So given this decomposition, we could easily find a wedge decomposable pair built out of spheres with a map in this category of weak freeness type. And from what I just said, I've got to get the same cohomology.
So that kind of splitting is something like a Mittag-Leffler or something?
Well, it's sort of like what you do is you basically put in one simplex at a time. Actually, Don talked about this. You look at the push out and you build up your simplicial complex one simplex at a time.
I know. But
and you can show by induction that you're going to get an isomorphism just carrying around the long exact sequences.
But my question is that can you translate that kind of thing in terms of into the Gauss-field conspectral sequence?
The answer to that is no, because the Gauss-field conspectral sequence makes intensive use of the ring structure. And this is definitely not as rings. The input to the Gauss-field conspectral sequence, you have to, at least the unstable, the Gauss-field con really uses actually the co-product, not the product. That's an integral part of making the tote, et cetera, et cetera. This does not satisfy that. Okay, so I'm sorry, I misunderstood your question. Well, oh, by the way, of course, it would work here. But you know, for that special case, I have the ring structure. You can actually write down the ring structure quite explicitly as in terms of the cohomology of the links and how they multiply.
This is always possible. There's always a homological.
It's only as a group.
There's always a homological wedge. Everything is homologically wedge decomposable.
Right.
And that's all.
Over a field, or if you assume a finiteness condition. I mean, a freeness condition, correct.
Not mention, Martin, that from the stable splitting, you can describe the ring structure, the cup product structure from the stable splitting. That sounds rather paradoxical. And then what we, in fact, in the proceedings of the field's thematic program, there is a paper that proves this homological wedge decomposability using symmetric products.
Yeah.
That's in the field. That's in the field volume.
So, and the point I wanted to make is that the proof I gave of the wedge lemma from the black box is the proof of why that works. There's nothing more in the idea. There's no other idea.
But then, since there are some proofs using, I don't know, commutative products or stuff like this, can everything be lift up to opera theory?
To what theory?
Opera theory.
Oh, that's a good. Actually, I doubt it for cohomology because you don't have enough structure to extend it to operads. Perhaps there, I don't know, but I would expect with the right words and the right knowledge, I think you could do it in that case, but I don't expect it to work here. So, good question. That would be lovely because, in other words, I'm making no claim about cohomology operations. As I mentioned, you do it by proving there's a cohomological wedge decomposable equivalence with wedges and spheres, et cetera. You've thrown away all the Steenrod algebra. So you can't see that in this cohomological version of the theorem. Yeah, right. There you can. Yeah.
Actually, if I could just say something, one thing about this is, let's suppose you want to talk about the cohomology of polyhedral products. Here's a polyhedral product, and you want to talk about the cohomology. That's already a difficult problem because you need names for generators. You need names for classes so that you can multiply them. And I think Martin will agree, the wedge lemma here allows us to give names to the classes in cohomology. And then once we have names for the classes, we can worry about how to multiply.
That's an important, because think of this as a way of labeling.
Just having names for classes in the cohomology of a polyhedral product is non-trivial.
Right.
Martin, please. Are there any other questions for Mark?
Can I turn my speaker off?
Okay, so I think we all enjoyed that. So may I ask you now, may I ask you now all to unmute and let's thank Martin.